All right, guys, in this video, I'm going to talk about one of the, in my opinion, most interesting things, and that is why in the world does the pH scale go from 0 to 14? When I was a student, I took that as face value. I was like, oh, okay, 0 to 14, la la la. But then when I became a professor, I started to really delve into it, and I was like, why in the world is it not 0 to 10? Like, where did this 14 come from? Everything else, in metric system and whatnot is based on tens. Why is pH based on 14? And so then I also started to think, well, why are we saying that neutral is 7? Like, where did that come from? Did someone just randomly decide that 7 was going to be neutral pH? Or is it actually based on something? So, it's totally based on something, which I just think is fascinating. So, we're going to delve into why is neutral 7? Why is the pH scale 0 to 14? And so, the first thing that we have to think about is, what does neutral really mean? Neutral means no acid, no base, no hydronium ion, no hydroxide ion. So, pure water, pure, deionized, distilled, beautiful water has a pH of 7. So, let's look and see what happens when you react water with water. I know this seems super weird, but this is actually happening all the time. Like in our water bottles, in water that we drink, water is actually reacting with other molecules of water. And the reason this happens is because water is special. Water is special for so many reasons, but one of the reasons that water is special is that water is amphoteric. What that means is that water can either react as an acid or a base, depending on what its partner is. So water is amphoteric. It can react as either an acid or a base. Depending on what it's put with. So if we take HCl, which is an acid, hydrochloric acid is an acid. When we put hydrochloric acid into water, hydrochloric acid is the acid, and water is actually acting as the base. Acids are proton donors, bases are proton acceptors. So the water accepts the proton from the hydrochloric acid to form hydronium ion. So in that case, water is acting as a base. But let's put water with ammonia. Ammonia is a base. That means water is going to be acting as the acid. So it just depends on what partner you put water with. It can either be an acid or a base. There are other things that are amphoteric. We'll get into those a little bit later, but water is the biggest one that it's amphoteric. So let's say that this water over here on the left is the acid. This water over here on the right is the base. We can do a proton transfer. The acid wants to get rid of its proton. The base wants to take the proton. So we're going to form hydronium ion and hydroxide ion. So water reacts with water to be in equilibrium with hydronium and hydroxide. Since this is an equilibrium, we can write the equilibrium constant expression. Products to their orders divided by reactants to their orders. So the equilibrium constant for this reaction is hydronium ion to the first power times hydroxide ion to the first power divided by water squared. Again, I can't emphasize enough. Watch those coefficients. We have two water molecules coming together. So the coefficient in front of water in the reactants is 2. So it's divided by water squared. Now, we're going to take water out of there. We did it before when we did the Ka. We said, well, water, 55 molar, it doesn't change that much. Also, water is a pure liquid. Pure liquids don't generally appear in equilibrium constant expressions. So we're just going to take water out of there and we're going to rename this Kw. Kw is equal to hydronium ion concentration times hydroxide ion concentration. This is called, oh, I know I have it written down, the autoionization constant of water. Autoionization constant of water. Okay, and so what was determined? This was determined experimentally, I'm pretty sure. I haven't delved into that too extensively, that's a better word for that. But the KW was actually calculated. So at 25 degrees Celsius, KW is equal to 1 times 10 to the minus 14th. So that's tiny. Again, okay, we're sitting here and I'm telling you water reacts with itself to form hydronium ion and hydroxide ion. But the equilibrium constant for that is 1 times 10 to the minus 14th. It is tiny, little itty bitty equilibrium constant. This is totally a reactant's favorite equilibrium. We just get teeny tiny quantities of hydronium and hydroxide present at equilibrium. Okay, well, here's the thing. Let's actually solve, right? Let's do the math. Let's solve for the pH at 25 degrees Celsius. So let me rewrite that equilibrium. Water reacting with water to form hydronium and hydroxide. And, oh, hold on one second. Oh, no, right. It's an equilibrium. We know that the KW for this is 1 times 10 to the minus 14th. We do not care about the initial concentrations of water. We have no hydronium and no hydroxide initially. The change, we don't care about water. Doesn't appear in equilibrium expressions. We're going to increase hydronium by X. We're going to increase hydroxide by X because the coefficients are 1. At equilibrium, we don't care about water. Concentration of hydronium is X. Concentration of hydroxide is X. We're going to say 1 times 10 to the minus 14th equals X times X. So X equals the square root of that, 1 times 10 to the minus 7th. That is hydronium ion concentration. So the pH is the negative log of hydronium ion concentration. The pH is 7. And so that's where we get neutral from, at 25 degrees. So again, we're assuming we're at 25 degrees all the time. We are not always at 25 degrees, but we assume at 25 degrees, neutral is 7 because the autoionization constant of water is 1 times 10 to the minus 14th. Now, this, in my humble opinion, is where things get a little bit trippy. This equilibrium is either endothermic or exothermic. Let's LeChat it in order to figure out if the equilibrium is endothermic or exothermic. So here's our equilibrium again. Water autoionizing with itself to form hydronium and hydroxide. And we'll be at 50 degrees Celsius. KW is equal to 5.48 times 10 to the minus 14th. Okay? So, what is the pH at 50 degrees? We can do the math again. It's an equilibrium. Initial concentration, we don't care. 0 and 0. Change, we don't care. Increase by X, increase by X. At equilibrium, we don't care. X and X. 5.48 times 10 to the minus 14th equals X squared. X is equal to 2.34 times 10 to the minus 7th. That is the hydronium ion concentration. So the pH is the negative log of 2.34 times 10 to the minus 7th, which gives us a pH of 6.63, which, again, you guys, is unbelievably fascinating to me. we think about water as being pure water, DI, pH of 7 the whole way. But as soon as we start to heat it up, we actually shift the equilibrium. And hot water is more acidic than cold water. So interesting. So now let's use this information to determine if the equilibrium is endothermic or exothermic. So we're going to Le Chatelier this. So what I mean by that is, okay, when we are at high temperature, we are more acidic. That means we have more hydronium ion concentration. So in order for a shift to occur, where do we add energy to get a shift to the right? Because that's what's going on, right? At 50 degrees, we added energy. And the physical observation that we can observe in the lab is that it shifted to the right. So where is that energy term? The energy term is over here in the reactants. We increase the amount of energy by putting it in hot water, and that shifts the equilibrium to the right-hand side. Energy as a reactant means that this process is endothermic. Energy is required. The delta H is positive. So that's how you get a pH of 7, and that's how hot water is more acidic than cold water. What's the most important take home for this? The most important take home for this is that the Kw at any temperature is the concentration of hydronium times the concentration of hydroxide. There's always a balance that's going on between hydronium and hydroxide in any solution. All right, so that's now hot water is more acidic than cold water.